Morning. So, how's it going? How's the lab? Wait, we do labs in this class? What is it? What is that? So, anybody have any questions? Fun activities they did over the nice long weekend? What? There was no break? I had a break in lecturing. Yay! So there's. So, all right. We are going to finish off the Lab 6 material, and today we will proceed on to the Lab 7 material. So, how this works is, so what I'm doing my darndest is to try to make sure that I have all the material that you're going to need to do the lab completely before you start the lab. Go away! That was a good knock.
A knock loud enough?
That was good. No wimpy knock. Okay. So, anyway, lab, basically how this goes is we've got lab 5. It's basically about stack frames and how you draw stack frames. Lab 6 is context switching and how to do process creation. Lab 7 is semaphores. Now, if you've ever had an operating systems class and you're starting to think about, okay, we're doing dining philosophers. No, we're not doing dining philosophers. We're implementing semaphores. We're not doing these weird abstract traffic light problems. This is how they actually work, and it's pretty cool. So we are going to be talking about how you switch between processes, how you create processes, how you synchronize processes. So Lab 5 is a 1-week lab, Lab 6 is a 1-week lab, Lab 7 is a 1-week lab, and they go fast and furious. For the most part, I give you the code that you're going to need to write. I give you code on journal files, and I'll also give you the assembly code in text format, so you don't have to mix up typing that sucker in. But you are going to have to type in the C code that I'm going to give you for this stuff. So I'm not giving you the code for like process creation. You're going to have to type that one yourself. The reason why is because you're going to learn by typing it. And I'm going to point out to you the number one error that killed everybody 2 years ago when we were typing process creation code. One little thing about pointer arithmetic that impacted things significantly. But anyway, so with Lab 6 and Lab 7, there are a couple of small little gotchas that are good exercises in how to think about things. I'll help you out. For the most part, the amount of code you've got to write is not very much. But so that will take us through the first week or so of November, and then we'll have Lab 8, which is on real-time scheduling, and that's really what we're building all towards. And after that, will be Lab 9 as the final lab, and we're pushing as hard as we can right now so that you guys can have as much time as possible on the last lab. And we're actually ahead of the pace a little bit, so we're doing pretty good. Questions about scheduling? All right, Mitch.
I have a question about the lab.
Okay.
So if we want to get assembly code that will actually enable us to figure out the calling convention, we need to have optimizations on.
Okay, so if you're trying to ask your compiler, what is the calling convention, do you need to have optimizations turned on or not? No, you don't need to have optimizations turned on. The calling convention is observed regardless of whether optimizations are on or not. I would suggest initially do not have the optimizer on. Okay? Other questions? Okay. So just briefly reviewing to get the brain back engaged to what we were talking about before. You remember we started talking about these slides and about how we have a process and it has a lifetime. Come on. Here we go. Okay, so processes are idle, they're ready, they're running. This is where we've allocated a data structure, but the process really hasn't been created yet. This is just a data structure that perhaps has been allocated and it's waiting to hold a task that we haven't created yet. Eventually it'll be created. Over here we have all of our processes that we've created are either in the ready or running state. Only one process can be in the running state. Everybody else is ready. So what we're talking about is the code that we need to build so that we can manage a set of tasks. By managing them, we need to be able to create them. We need to be able to swap them in and out. We need to be able to schedule them, decide in which order the tasks get the CPU or if there's some type of priority associated with them. So this is where we started talking about the nuts and bolts of how we're going to actually in code describe tasks. Okay, so just briefly, we've already shown this, but we've got to understand what this code is in order to understand the process creation stuff that we haven't talked about yet. So if you remember, we defined an enum, one item inside this enum for each state in our process state machine. So a task can be idle, ready, or running. We're going to say this is a process state, so we're going to declare variables of type process state that hold a value that indicate what is the state that the process is currently in. We have a type called context, which is typed def to be a pointer to an unsigned integer. Okay, and we'll use an object or a variable of type context to point to where the top of our stack is once we push the context of the process onto it. We've got this structure here that keeps track of our process. So this struct, it's typed def to be named process. It's got two fields, a context field called context and a process state field called state. So this is the structure that we're going to use to track our processes and figure out, or not to figure out, but to hold all the processes that get created, or each individual process gets created. Okay. A process, what does it look like in code? It looks like a function. It's a function that can call other functions. It's just regular old C code. All of our processes are compiled together into one executable program. Okay? So a process has an entry point. This is the beginning line of code, the first place where it runs when it executes. The entry point, because of the way that we're structuring our processes, really is just a function. So we're going to define a function pointer called process function that points to the initial assembly instruction or the initial label or the function that we're going to use as our process. So this is a type def. We're defining the type process function as a pointer to a function that returns void and takes a single integer parameter p. All right. How do we keep track of all the processes? We keep them all in a FIFO. You're going to hack your Lab 0 implementation to create a process FIFO. We'll call that FIFO a ready queue because it really is a queue or a FIFO of processes that are all ready to run. And we have one other pointer to a process that is our running process. So all of the processes that we have created will all be on the ready queue except for the running process. The running process will be pointed to by this pointer called process running. It is of type static volatile process star. So it is a pointer to a process that's been declared volatile because we don't want the compiler to assume anything about it because the value of this guy could change in the middle of could be changed by an interrupt service routine, and it could be accessed outside of an interrupt service routine. So we don't want the compiler to assume anything about this variable because it can change outside of the normal flow of the program. We declare it static to localize, because this is a global variable, we want to localize its access to the file in which it is defined. We also have process FIFO, which is what you're going to define when you hack your Lab 0 code. We'll have static process FIFO star ready queue. Why doesn't ready queue need to be volatile? Will the contents of the ready queue change inside an interrupt service routine? If you think about it, if I've got an interrupt service routine that does a preemptive context switch, I've got to pull a ready process and a running process, and I've got to make the running process be that ready process, and the running process that I've currently got, I've got to make it a ready process. So I'm just pulling one guy out of the ready queue, making him the running process, take the old running process and making him a ready process, so swapping them. So not only do I context switch them, but I have to swap how I'm keeping track of them. So the running one will go in the ready queue, a process in the ready queue will go be pointed to by process running. So therefore, I can change the contents of the ready queue inside an interrupt service routine. Therefore, why am I not declaring the process FIFO as volatile? Tony? Okay, so the ready queue object. You notice I subtly said the contents of the ready queue. That is different than the ready queue object itself. Ready queue is a pointer to a queue. The queue's contents will change. That effectively needs to be volatile. But the pointer to that queue won't change. I'm only ever going to declare and allocate a single ready queue object. Okay? So I'm not going to have multiple ready queues. I'm not going to change the value of this pointer. I'm going to change the value of the structures that are pointed to by the contents of the structure pointed to by this ready queue. Okay? So I got to go one level of indirection down the chain in order to get to the things that I can change during the interrupt service routine. This guy will never change. If he does, then it's a bug. Yeah.
You said it points to the ready queue itself, right?
So that is a pointer to the ready queue itself. And then the contents of the ready queue can change, but the ready queue object, which is just a data structure, think back to how you defined your FIFO. Okay, it was just a structure with a head pointer and a tail pointer. That structure will not change. What the head pointer points to and what the tail pointer points to, that can change. But the structure that holds the head pointer and the tail pointer won't change. Okay? You have to be judicious in your use of the volatile keyword because it'll slow your program down. Okay? It's not just, well, for the sake of paranoia, I'm going to declare everything volatile and hope that it all works. You are going to be faced with the temptation during this class when you've got bugs in your code and you're thinking it's some weird process interaction bug. Let me just declare everything in the whole darn program volatile, and maybe that'll fix it. That won't fix it. Okay? What you need to do is understand what is the impact of volatile, when should I apply it, and why. And you will gain more experience with that as time goes on as I talk about it some more. Okay. We have a prototype of the context switch function. We have prototypes for the various functions we're going to define: proc create, start scheduler, schedule next process. Okay. So skipping to the end first. This is the code for schedule next process. Did we talk about this one last time? Did I show you schedule next process? That was so long ago, Dr. Eames. What are you talking about? It was like Thursday. I actually think I did show you the code, because I think I got down to proc create, and we didn't show proc create. Maybe I did. Maybe I didn't. Well, anyway, given the blank stares on your face, it's irrelevant whether I showed it or not. Okay. Schedule next process is the name of a block of C code that is our scheduler. Okay. So this is the other entity that decides which task gets to have the CPU next. Context switch is not the code that decides which task gets to have the CPU next. If you remember, when we call context switch, we've already decided I'm going to swap the current running process out. I'm going to swap this process in. Schedule next process decides which is the process that we're going to swap in. It calls the context switch to do the swapping, but it is the higher level entity that makes the decisions about which process gets to have the CPU next. Okay? So it works in conjunction with context switch. Context switch is very limited, and all that it does is saves the current running process's context onto its stack, unloads the new process's context into the processor, and runs the new process. But the decision of who that new process should be, that's made by the scheduler. Okay? Right now, for Lab 6, we are implementing a very simple scheduler. It's called a round robin or a FIFO scheduler, a fair scheduler. And what that means is that all the processes that we create all get equal access to the CPU. Or in other words, the scheduler just maintains the process FIFO, and we cycle through those processes in the ready queue in order. So we say that who's the process that's been waiting for the CPU the longest? When we do a context switch, that's the guy that gets the CPU next. Okay? So if we only do preemptive context switching and all processes end up being able to execute their whole time slice, the time slice is equal to the period of the timer interrupt. So we run the timer interrupt, swap a new process in, that process gets to run until we run the timer interrupt again, then we swap a new process in, that process gets to run, then we swap a new process in. So we're always just cycling the running process back to the back end of the ready queue, taking the front end of the ready queue and putting it into the process that's running. How do we do that part? So this is what this code is trying to accomplish. Schedule the next process. We declare an integer R. We declare two pointers to processes, old P and new P. So first thing that we do, we disable interrupts. Why do we disable the interrupt? Because if you're involved in swapping your process out, you do not want to call your timer interrupt, which could end up calling this code again. This is what you call non-reentrant code to the nth degree. You do not want two threads of execution in the middle of this code at the same time. It will mess it up. Why? Well, what happens if you are in the middle of swapping one process out and swapping another process in, and all of a sudden you start monkeying around with your ready queue again? You could end up losing a process. Okay? So we are very paranoid when we have schedule next process, when we're going to start monkeying around with the internals of your process queues. We disable the interrupts to prevent the possibility of ever executing this code and getting preempted while we're doing it. Okay? Mitch?
I think you're talking about this. So when interrupts are disabled, do any interrupts that fire get queued up into the...
So the question is, well, what happens if we're in the middle of processing our scheduler and the RPM interrupt becomes enabled? What happens to that? Do we just miss it and it goes away? Or do we somehow remember that it wants attention and later on go and process it? So there's a 1-bit FIFO. Or there's a 1-bit history for each interrupt. So what we do is we, whenever an interrupt source comes up and says, I want attention, we latch that and we remember that it wants attention. So as soon as we enable the interrupt again, all the interrupts that are pending will be handled in the priority order as dictated by the VIC, and eventually this guy will get serviced. The problem is if you get 2 interrupts before you, or more interrupts before you get to be able to handle it, you'll miss the subsequent one. What you'll do is you guarantee that you will at least handle that interrupt. So you remember that this type of interrupt occurred, and it'll stay asserted until you service it. Okay? All right. So we disable the interrupt. We say old P equals process running. And so what this does is it takes my local pointer, old P, and I'm going to point it at whatever process running points to. This does not point old P at process running. It points old P at the process running points to. Okay? So old P is a pointer, process running is a pointer. They both point to the same spot after this statement. Okay? The next thing is we say R equals FIFO remove ready queue address of new P. So this is what I'm doing to access my FIFO to say, give me who's ever popped the FIFO, give me who's ever been on the FIFO the longest. Tony.
1 and 1.
Okay. So I pass the ready queue. This is the pointer to my FIFO, and I pass the address of new P. So what this function will do is it'll point the new P pointer at the process that's been waiting the longest on the ready queue, and it'll remove that from the ready queue. I get the return value R. And I say, if R not equal to FIFO failure, then proceed. If R is equal to FIFO failure, I'm not going to switch. Because if the remove process, or if the remove fails, that probably means that the FIFO is empty. If the FIFO is empty, I can't switch to anybody, because my running process is my only process. So I'm only going to switch if there's somebody in the ready queue. So I'm going to check to make sure that my remove succeeded. So if I didn't fail during remove, then go to the following. Old P is my old process. I'm going to mark its state as ready. I'm going to mark the new process's state as running. I'm going to insert the old process into the ready queue. Then I'm going to set process running to point to whatever new P is pointing to. And I'm going to invoke the context switch. Okay? So this is all housekeeping stuff. So I'm going to mark the state of the processes, update the state of the old process and the new process. I'm going to insert the old process, that's the one that's currently running, into the ready queue. I'm going to point my process running pointer at this new process. Up to this point, before you call context switch, the old process is still running. Even though I've said old P state equals ready. Just by setting the state variable of the old P to ready doesn't make it ready. What makes it ready is when I swap it out. Okay? I don't swap it out until I call CS. So CS has to be called in order for the context switch to actually occur. All of this other stuff is housekeeping stuff that has to be done so that when I later go back in my scheduler later on and maybe I want to query the state of the current process or a different process, I've got the state maintained consistently, or when I want to go and swap a new process back in, I've got to make sure that my ready queue is maintained appropriately. So these steps are necessary, but still, I don't actually run the new process until after I'm done calling context switch. Okay, on context switch, the parameters that we're passing are significant. What I'm passing is the address of the context field of the process that old P points to. Okay, and then I pass the context field of the process structure new P points to. Okay, so again, I'm passing the address of the context field of the old process. So what that does, CS will push all the state of the currently running process onto the stack, and then it'll store in this address that I pass here, it'll store at that address the top of the stack where it put the old context. So that way I remember, where did I store old P's context? Over here I'm passing a copy of a pointer to where new P's context is stored. Okay, so I pass that by value on the stack, and from that location, CS will then unwind the stack, the context of that new process I'm swapping in, put all of its saved state into the registers, and then we'll start to execute. We'll jump to the wherever it was that process was running when it was swapped out. Okay? So this brace right here is the closed brace from that if statement. And then I explicitly do not enable the interrupt. Okay? So I only disable the interrupt up here, but I do not re-enable it. Why don't I re-enable it? Because I can call a scheduler from an interrupt service routine. I do not want to enable the interrupt inside an interrupt service routine because I don't want to have an interrupt interrupting an interrupt. Why? Because I would get thoroughly hosed because my interrupt stack is not set up right. Okay? If you remember all that ISR's code where we had to deal with making sure that the interrupt is handled inside IRQ, we're in IRQ mode, and we have the IRQ mode stack pointer, and it originally points to the shared stack shared by all the processes for the IRQ mode stack. We keep track of that stack pointer, but we also make sure that we have our IRQ mode stack pointer pointing to our process's local stack. And because of that whole shenanigans, if I interrupt an interrupt service routine, that's just, it will be a disaster. Just things would work very weird, and you would be debugging for days. Okay? Be careful when you enable the interrupt. Now, the next question becomes, well, what happens then if I get back? Is there a way that I can get back to my process if I got interrupted with interrupt disabled? Well, yes and no. So if you remember how we enable and disable the interrupts are macros that I provide you, but what they do is they write to the CPSR register. So the CPSR contains these bits that say whether or not IRQ interrupts are enabled and whether or not FIQ interrupts are enabled. So by virtue of what the interrupt state was set when we swap the process out, that will restore its state. And likewise, when we restore the state inside the end of ISRs where we pop the saved program status register into the CPSR register, that'll restore the state of the interrupt. So we will be okay if we don't enable the interrupt right here. Okay. So this is schedule next process. Basically, all that we're doing is we're just taking the oldest waiting process out of the ready queue. We're making that be the running process. We're taking the currently running process and putting it onto the ready queue. And then we call context switch. Straightforward stuff. We'll make this a little bit more complicated in subsequent labs. Okay, so now what we have is start scheduler. So what start scheduler is it's a function that, well, you can probably guess what it does. So this is a function that you call after, so let's suppose that we're going to create 5 tasks. We're not going to support dynamic task creation. We will eventually, but let's suppose that we don't. You would initially create the 5 tasks with a proc create function that I'll show you in a minute, and then you'd call start scheduler. And inside start scheduler, the scheduling machinery would proceed and would run. And then whether you're doing preemptive or cooperative, schedule next process would be called at the appropriate intervals, and you'd swap between those 5 tasks. But this is the guy that effectively starts your operating system. So what do we do inside Start Scheduler? It looks a whole lot like a Schedule Next process, but we haven't started any process. We're not switching from an old process to a new process. We don't have an old process. No process is running. So, but effectively what we have is, you know how you're running main and you can print out hello world on your board? You can run code, but it's not a process that we've created with our proc create function. It doesn't conform to our operating system, but yet still we have control of the processor. We can run a C program, right? So in some sense we kind of have a process, but it's like this rogue process, this main that just runs. And we want to run in the context of our scheduler, our process, our operating system. So we're effectively going to swap out main, or however you want to think about it, and we're going to swap in our first process. So what we have is a pointer called first P, and we're going to define a context variable called C. We'll disable the interrupt. We'll remove from the ready queue a process, which is the process we're going to first swap in. This says if R not equal to FIFO failure, that means, you know, we're not going to swap to anybody if nobody's there. So if we succeeded at pulling a process out of the ready queue, we set the state of the process to running. We set process running equal to first P, and then we call context switch, where we pass the address of C, and we pass by value first P arrow context. Okay. What this does is it says I'm going to push all the state of the processor onto the stack. And I'm going to remember where that state is by pointing C to it. And then I'm going to unload the context of first P, starting at this address that I get passed, and I'm going to put all that stuff into the processor state and jump. Start running the first process. Okay. Now a question that I have for you is, what do we do with C? C is a local variable here. This context switch causes us to jump away from here. We never return from here. We never come back here. So we effectively push main's context onto the stack and throw it away. Likewise, we throw away the original stack. So we don't ever use the original stack that you guys have been pushing and popping stuff on the whole semester so far. So this is just a holding place for storing main's context, and then we forget it from that point forward. When the program ends, you don't go back here. No, the program never ends. We are embedded processing, so therefore, you know, I don't want my anti-lock brake system to stop. That'd be bad. Okay. So here's an example process. We'll call it test process. You remember our entry point was a type def, a pointer to a function that returns void and takes an integer parameter P. This is an instance of one of those types of process, or one of those types of functions. The name is test process, returns void, takes an integer parameter. The fact that it's named P is just coincidental. Okay, so all that we're doing is we're going to printf. We'll say process %D is running. We pass P as a parameter. So we're going to pass in the parameter to test process its ID, some integer that distinguishes it from other processes. Okay. So we'll disable the interrupt, call printf, enable the interrupt, then call schedule next process. Why do we disable the interrupt and enable the interrupt around the printf? What happens if you print from an interrupt service routine and you print from main? Y'all have played this game before. Does it work right? Does it work? Does it break your processor? You let the smoke out? Mitch says it doesn't work. You let the smoke out of the processor if you print. So you physically destroy the processor if you print from the ISR and main. You don't let the smoke out. Okay. So it physically works. What happens? Heap stack collision. Okay. So if you take the precautions against getting the heap stack collision and do a whole bunch of printfs before you enable your interrupts, you won't get the heap stack collision. So, but did your print come out looking like you want it to look like? Or does it come out jumbled? So, I'm kind of uncomfortable with this, guys. Y'all should be on top of this one. Is that, how about, SPRINF? That was a Lab 4 question, right? Are we having trouble because main's not swapping back in your heads? Is this what's going on? Are we having a context switch fault? Is the ready queue empty? Is SPRINF re-entered? Anybody care to offer a contrary opinion?
No.
I would say that you didn't test it thoroughly enough to determine absolutely whether or not it was re-entrant. But the test that I told you to run indicated, yeah, it was re-entrant. So long as you don't print to the same buffer in main that you do in your interrupt service routine. Is printf re-entrant? Why is printf not re-entrant? Because it messes up. Okay. Thanks. What's the non-re-entrant part about printf? Serial port. Okay. If you have 2 threads executing, if it were re-entrant, you'd have to have 2 serial ports. If you had 3 threads executing, you'd have to have 3 serial ports. Similarly, there's all those internal buffers that can get all messed up by printf. Okay. By printf executing in a non-re-entrant fashion. All right. So, why would we disable the interrupt around here, around this printf? Why would it get jumbled? Am I going to call test process from an interrupt service routine? Okay, so I could get an interrupt while printing, but let's suppose that I'm not doing any printfs inside my RPM or inside my PIT. What's going to cause this to get all jumbled up? Change in P? How can I change P? What's going to happen in an interrupt? Yeah. So that's the problem, is every time I get an interrupt, I could end up giving a context switch. So it's not the interrupt that's going to print that's going to mess me up, it's another process. Okay? So I could get into the middle, if I don't disable and enable the interrupt, I could get in the middle of a process, get an interrupt, get to a context switch, swap in another process that it does printing, and that could collide with my print. So it's the non-reentrancy that's messing up now 2 tasks that are running, 2 processes that are running. So I disable the interrupt to guarantee that no other process is going to mess up this printf. So I run this printf to completion. So in other words, this printf executes in a sense of what we call atomically. It executes atomically with respect to any other process. It is this printf, because we're disabling and enabling the interrupt around it, it acts as if it's a single instruction. It acts as if it can't be interrupted in the middle. It executes as if it's a single, one, indivisible operation with respect to any other process. So no other process can execute in the middle of that printf. That concept of being atomic with respect to other processes will be important when we talk about semaphores. What does this called the schedule next process here at the bottom of this code do? That's a yield. I swap myself out and let somebody else run. Does this say that that's the only way that I can swap this process out, or can I swap it out with an interrupt? Nothing saying I can't swap it out with an interrupt. Okay, so this code right here supports cooperative swapping with that schedule next process and preemptive swapping by virtue of the fact that we call schedule next process from PIT. Okay, the next final issue with this is how do we create a process? So we know what the process code that we're going to run looks like. We know how to swap a process in. We know how to start our scheduler. We know how to run our scheduler. We know what our scheduler does. We've defined all the declarations that we need. Now we need to be able to create a process. Okay, before we dig into the process code, we're going to go back to your favorite, the context switch code. I'm sure this is what you spent your weekend working on. Okay, so if you remember the context switch code, we save the state of the old process onto the stack, and then we restore the state of the new process. what does the stack look like right before we swap it in? We drew multiple stack frames of this guy. Okay, so as we went through this, we drew what the stack frame was looking like, and then we ended up at this location here where we have stack data, registers, CPSR, and pointer to self all on top of the stack. We drew this stack frame saying that this is what the old stack looks like. For the process we're swapping out, this is what its stack looks like. What does the process that we're swapping in look like? Just like that. Okay? So we'll have some stack data or something on the stack that we don't really care about. It's got its registers saved in a particular order. It's got the process's CPSR value, and it's got a pointer to self sitting on the top. So every process that we swap out with our context switch code will end up looking like this on its stack. Every process that we swap in has to look like this if we're going to have the context switch code swap it in correctly. Okay? That is a very important point. The process that we're swapping in has to look like this. What if we're just creating a process? Well, if we're going to use context switch to swap it in, which we are, it's got to look like this. So we've got to kind of, in some pseudo way, create a stack that looks like this in order to use context switch to swap it in. So this is kind of walking backwards into our context switch. We're going to, right now, up to date, we've assumed that every process that we're swapping in was swapped out by context switch. So we, in some sense, have to create a situation to where the context switch code can't distinguish between a stack that we create initially and a stack that has been created by the context switch code. So we've got to make the stack of a process that we create look like that in order for the context switch to swap it in correctly. Okay, first question I have. We push on the registers onto the stack. In what order are those registers pushed onto the stack? We use an STMFD. That STMFD looks like this up here. Okay, so when we store it on the stack, we do an STMFD, SPBang, R0 through R10, FP, SP, LR, and PC. The LDMFD at the bottom loads them back off. So if we're passing a pointer to a stack that we are creating outside of a context switch, these statements that unload the stack have got to work correctly. So the order in which this code expects data to be on the stack, we have to supply correct data in the order that this expects in order for us to be able to swap in a process that we're creating. Okay? So right here, if you remember, what we do is we pop from the top of the stack. So, okay, R1 is pointing to the top of the stack that we're swapping in. We add 4 to R1. What that does is it just removes the pointer to self from the top of the stack. We never actually use the pointer to self on the top of the stack of the process that we're swapping in. Okay, so we just remove that guy. So we've got to have something sitting at the top of the stack that we're passing in, but it doesn't have to be anything valid. There just has to be something there. Okay. The next thing that's at the top of the stack is the CPSR. The next thing that's at the top of the stack are all the registers. R0 through R10, FP, SP, PC. There has to be slots in there that are set at the correct spots in order for this to be able to unwind correctly. Tell me.
You do R0-R10 and then SP, SP, PC. You do R0-R16.
So, okay, the question is, can you do R0 to R16 instead of R0 to R10? No, because there is no R16. You could do R0 to R15.
Oh, yeah.
So the STMFD supports that, and the LEMFD supports that.
I was just wondering if the alias is going to be the other.
Technically, PC, SP, FP are the aliases. These are the real register names, the R0, R1, R13, and all that. So yes, it's kosher. But if you look carefully, we're not using all the registers there. Okay. So the question that we have to ask ourselves is, in what order are these registers that we pushed onto the stack? In what order are they on the stack? If you remember, I told you that when you use an STMFD and you pass a set of registers, the lowest numbered register gets put at the lowest address on the stack. That means if we draw our stack frame, it's highest up on the diagram. So R0 is at the top spot. PC is at the bottom spot. All right. Now that we've got that swapped back into our poor brains, we're going to look at process creation. Okay. We're going to, in order to instantiate a process, we've got to allocate a space for it to have its stack in. Okay, so we're going to declare an array called process stack 1 and process stack 2. We can declare a bunch of other ones. 1024 slots long. Nothing magical about 1024. You may want it bigger, you may want it smaller. How much stack space is your process actually going to use? If you declare it too big, you're wasting space. If you declare it too small, you're setting up yourself for a very, very big disaster called a stack overflow. That is very difficult to track down. Okay? You remember we said we had a prototype of the proc create. It takes 3 parameters. So if we want to create a process, this is how we do it. We call proc create. We pass it the name of the entry point function, which is test process. We pass it the value that we want to have be the test process parameter that we pass to it. So we're passing a 0. Test process will be invoked as if 0 were passed to it. And then we pass it an address for the stack of that process. Now, if you remember, stacks grow from high addresses to low addresses. So we've got to pass the highest address of our stack array. The highest address of our stack array is the address of the ending element in the stack. So we pass the address of process stack 1, slot 1023, because that's at the bottom of the array, okay, or it's at the end of the array. The address of this element is the highest address corresponding to the stack array. Okay, because we're using this as a stack, we're going to go from 1023, 1022, 1021, all the way up to slot 0. Hopefully you never get to slot 0. But this is a little bit backwards than what you're used to for accessing arrays. Okay, if we want to create a second process, we call proc create, we pass it test process. Both of them will have the same entry point. We'll pass a 1. This means we're both processes. They will be different processes. One of them will be executing with parameter 0. The other one will be executing with parameter 1. We pass process stack 2, the address of its 1023rd slot. Okay? So entry point, parameter, pointer to the stack. After we've created our processes, eventually we call start scheduler, and then we have this printf that said this should never print. Okay. Recall, link register, LR, contains the return address, SP contains the top of the stack, R0 contains the value of the pass parameter, PC contains the address of the first instruction in test process. Okay, so we need to make sure all of that happens when we do this, okay? So in the real context switch, when we swap a process out, the STMFD puts all the right stuff in the right spots for that. But we need to make sure that it happens because we can't use the context switch to create the stack. We have to create the stack in an alternative way. We're creating it with C code. We've got to push stuff onto the process's stack, so we're going to define this push macro. So this push macro just acts like a push instruction in assembly, but because we're using it in C, we have to have a macro to do it. Okay. Dot create. We pass the entry point in F, we pass the parameter in P, and the pointer to the stack in stack. Okay? We declare a pointer to a process, an integer I, and an unsigned int value. These guys we will use. First thing that we do, we have to allocate space to hold the process that we're creating. It has to have a process data structure. We have to allocate space for that process data structure in some location that won't be whacked by other places. Where do we want to allocate the process's data structure? Well, we already have this stack space that we've guaranteed is going to be unique and separate from everybody else's memory. So we're just going to allocate the process data structure on the stack. So what we do is we decrement from the stack enough space to hold the process data structure. We've got this funky addition right there that makes sure that if stack is on an aligned 4-byte boundary, that we subtract off enough space that we have enough space to hold the process data structure, and that the pointer that we return will be aligned on a 4-byte boundary. So the result is stack. So we have size of process plus size of unsigned int minus 1, all divided by size of unsigned int. So that gives us enough space to hold the process. Then we point new P at stack. So we've pushed on the stack a process data structure, and then we point new P at that spot. Next, we start to push the registers onto the stack. Now, if you remember, registers get pushed on. The lowest number register gets the lowest address. The highest number register gets the highest address. So it's the thing that gets pushed on first. So we push things on in the right order. So we push on a 0 in the PC position because we're just going to pop that guy off anyway. In the PC position, we don't pop this into the PC when we're done. Remember, we pop the link register into the PC when we're done. So we just have to have this guy on a position in the stack. We push F onto the stack. This guy gets pushed on in the position that is the link register position. This is the guy that will get popped into the PC. This is the return address. So we're going to effectively call our entry point by returning to it. Okay? This is different than when you call a function. You call a function by mentioning the code explicitly in a BL. Here, how we're going to call our entry point function is we're going to put the address of our entry point into the link register and then pop that into the PC. So it's like we're going to return to a new spot. Okay, then what we do is we calculate value is equal to unsigned int stack plus 8. This right here is the bug that killed everybody 2 years ago. If you don't have this unsigned int, it's not going to work because it'll do pointer arithmetic instead of regular arithmetic. So unsigned int stack plus 8. So we just pushed two values onto the stack. What we're doing is we're calculating the address of the bottom of the stack in order to put the value that represents the bottom of the stack onto the stack. So we push onto stack value. This is in the SP position. So this is what we want the stack pointer to point to after we pop all the registers. Next thing, we push a 0 onto the FP position because we don't care what's in the frame pointer. Then we push 10 zeros onto the stack for R10 through R1. Then into the R0 position, we put P. We put a 53 in for the CPSR. We push a 0 on the slot for the pointer to the top of the stack. We're going to pop it off anyway. Then we set up the context and state fields of new P. And then we insert the new process into the ready queue. Note that we don't swap to it because we're just creating the process. So all this does is push all the registers onto the stack in the right spot so that when CS pops them off, they end up in the right spot in the state of the processor. And then we jump backwards to our entry point process, and the program starts to run. So this is a diagram of what the created stack looks like. Here's an explanation of what 53 means, and you're merrily on your way. So, thank you. What does Lab 5 do tomorrow? You can try that.
Well, I don't know.
I can do it tonight.
Yep.